Thanks, Chaz. Okay, hey everyone. So yeah, today I want to talk to you about direct imaging and spectroscopy with JWST. I really want to emphasize that these things are like intertwined together. You can't have one without the other, really. So to kick off, I'll just do a brief introduction. So Jason illustrated earlier this week this idea of direct imaging, where we're trying to directly resolve the light from a planet around its host star that has its own challenges. And really, I want to emphasize, whenever I say imaging, you look at an image like this and you think, okay, we're getting photometry, but really at the same time, spectroscopy is totally possible too. If the planet is sufficiently far from its star, it's easier. And if it's a little closer, then maybe it's a little more difficult. But really, spectroscopy and imaging are both things we can do with this technique. So, why are we interested in this population? Well, when you look at the planetary population in general, in terms of its sort of mass and semi-major axis, we see that imaging is really our only opportunity to characterize these outer planets, the outer architectures of planetary systems. So really, we need to make the most of that so we can detect these objects and really understand the full population of exoplanets that exist in our universe. More so, on top of this, and kind of linking to the previous talk that Nicole gave, when you break this up into just the methods we can use to characterize atmospheres, what we're all thinking about, we only have transits and imaging. So more so, imaging becomes even more important, right? Because we can't just characterize the stuff that's close to the star and maybe is heavily irradiated. We also need to explore these different atmospheric regimes that may be colder, that may be, dominated by the internal heat from their formation rather than this intense stellar irradiation. So with that in mind, I think it's good to just take a step back and pose the question, okay, great, we want to study these planets, but why should we be studying them with JWST? What advantage is it going to give us? And for me, really, I've talked about this a lot. I think it's kind of three key things. The first one is sensitivity. We've put like a giant 6.5 meter telescope in space, and that gives us a big advantage of just detecting really faint things. So when you're thinking about something like an exoplanet, that advantage is a very big one. Secondly, we have wavelength coverage, and this kind of has a twofold advantage for us. Firstly, planets in general, their emission is going to peak in those infrared wavelengths. So if we can get sensitivity in the infrared, in the mid-infrared, then we're in a regime where we can start to really detect these planets more broadly. And then, of course, as you've seen throughout this whole week, all of these different spectra you see, just expanding our wavelength coverage gives us an advantage in terms of characterizing the atmosphere in more detail, digging into more molecular species, more atmospheric processes. And then the final one is kind of the obvious one, but is quite important. We have this incredible versatility with JWST, where we have all these different instruments, different modes that are really, to some degree, in many cases, bespoke. They're designed for exoplanet science, particularly for imaging. So having that capability is just gets us off the starting mark, and lets us perform these kind of observations. So really, to kind of sum this up, I want to emphasize, it's not one key quality here. It's not one thing that makes JWST great. It's this holistic view. It's that we have the capability to do these kinds of observations in a new wavelength range that's really advantageous, and we can get really high signal to noise, really high precision measurements at the same time. Okay, so moving on, I'll start talking about imaging just to begin with. And a good way to start is just to return to this and realize, the first thing we can do is we have this existing population, so we can try to characterize in greater detail the planets that we already know exist there. That's something that we really kickstarted off with the early release science program last year for this object HIP 65426b. This is your kind of classic directly imaged object. It's super Jupiter mass. It's very young. It's mostly that temperature you're seeing. Most of that energy is from its formation. And it's really what lets us detect it. And we've had plenty of observations of this object already from the ground. You can see here, we get sort of decent characterization in the near infrared wavelengths. But as you start to move towards these longer wavelengths, the picture becomes less clear. We start getting limited more towards photometric techniques. And the precision we're actually getting on those measurements isn't exactly tightly constraining. So what we wanted to do with this program, as well as just understand how well these modes are working on JWST, is to start thinking about, okay, what can we do in terms of characterizing this atmosphere? What constraints are we going to get? So that's what we did. But the first thing that you end up seeing is just, when you get these images, is just a ton of residual stellar light in the image. And Jason pointed this out earlier this week, but we as well need to go through a process to kind of subtract this away, to kind of dig through the light and uncover the planet in the image. You know, when you look at this right now, I don't think many of you could really predict where the planet is. So the way we do that is we go and pick a different star on the sky that's maybe similar in nature to HIP 65426. We perform the same observation, and that characterizes that spatial intensity profile, and we can subtract it away. And the result is that we get these really nice, clean detections of the planet. So on the left, you're seeing one of the images from NIRCam, and on the right, you're seeing an image from MIRI. And really, I just want to linger on this to emphasize, you know, you'll look at this and you think, wow, this looks kind of weird, you know, this like a hamburger, and then maybe there's some like disc around this thing on the, all of that is not astrophysical, you know, it's not like moons or discs or anything like that. It's just the optical components of the telescope itself. It just ends up creating that PSF shape. So we did these observations actually in 5 filters with NIRCam and 2 with MIRI, and we were able to get really nice clean detections in each of them. But at some point, you know, you have to step away and go, okay, let's stop looking at the nice, pretty pictures, and let's actually try and estimate, you know, how much flux are we receiving in each of those images from the planet. And that's what we can do here. This is what you're seeing, this kind of spectrum. So again, the black points here are what we already had from the ground, and then the orange points are these new data from JWST. And there's a few sort of key things to think about. These points in the near infrared here, sort of from 2.5 to 5 microns, you'll see that you can't really see the error bar. That's just because the precision of JWST compared to what we have from the ground is just really groundbreaking and makes a huge difference. You know, we're not bothered by the atmosphere. We're not trying to, you know, calibrate the telescope with adaptive optics or anything like that. So we get a really clean, precise measurement of the atmosphere. Secondly, you see these points out here. These are the 2 MIRI measurements, which are really quite exciting to get, because it's the first time we've been able to characterize directly an atmosphere beyond 5 microns. And that's important because, you know, now we're in a regime where we're really characterizing the full luminous wavelength range of exoplanet atmospheres. That helps us look at a variety of different atmospheric species, but also lets us constrain the bolometric luminosity for this object. And for many of these, you know, we have an age as well, so we can start to tie that to evolutionary models and start to constrain those as well as the atmospheric models, see how they compare, see where they agree, and see where they disagree. So moving back here, you know, that's what we can do for a planet right now, and we can start to perform those observations for all the planets we know. But really what we also want to think about, I think, moving forward is, you know, okay, how can we expand this population and look towards maybe detecting new planets and characterizing those planets as well. And there's sort of 2 opportunities here in my mind. The first, which I think is a little more modest, is this opportunity to try and overlap with the radial velocity population or maybe the astrometric population to detect maybe colder and older planets for the sort of first time with imaging. These are going to be things in new atmospheric regimes. You know, they're going to be very old, but still dominated from the heat from their formation. So in sort of a very similar atmospheric regime to many of our own solar system planets, so the solar system giants. There's not many objects we can do this for, but there are some, and, you know, we can predict, you know, based on that radial velocity signal and astrometric signal where it should be on the sky. And we can perform simulations, and we do predict, you know, we will start detecting these planets moving forward, and there's cycle 1, cycle 2 programs to do this already. The bigger advantage in my personal view, though, is this opportunity to push downwards into this sort of quite obvious blank space in this plot. You know, it might well be that there's not a huge amount of planets out there, but the reality is we have 0 actual empirical constraint on what the occurrence rate of planets below sort of a Jupiter mass at these wide separations is. We've never explored it, but I think it will be exciting to do so, and I think will provide us some really new exoplanetary benchmarks. So we can do this. Here is from some green lines, just a collection of simulations of different stars that may be amenable to sort of characterization and imaging of low mass planets. And you see in the red line, this is the lowest mass exoplanet we've detected with direct imaging. So really we're getting to sort of order of magnitude improvement in the sensitivity in terms of mass space. So it really is this opportunity, I think, of a long-term timescales for JWST to start characterizing these objects. One nice way to do that is to not do a blind survey, but maybe do a targeted survey. And you can start to look at these really lovely disks we've seen with ALMA. You know, we take these images of them and we see this really interesting spatial structure, these gaps, and sometimes spirals as well. And one leading theory, you know, is that it's actually planets in these gaps carving out the material from the disk and producing this structure we see. And what you can do is you can make some assumptions, you know, okay, how massive is that planet going to be to carve that material away and produce this spatial structure we're seeing? And what we find actually is many of these objects kind of lie in this sensitivity regime that JWST is now providing us that we didn't have access to before. There are already programs to do this, to kind of explore these disk systems in greater detail, to kind of dig into and try and figure out, you know, is it indeed a single planet carving these gaps? Maybe it's instead multiple planets, or a different physical explanation. And then finally, as I've sort of alluded to a few times, you know, early on in these first few years, I think many of these observations are going to be in the nature of this kind of green point here. We're going to be going in and just trying to detect a planet for the first time. But JWST really does give us this characterization potential as well. And I think that's really the long-term value that's going to give us, where we can follow it up with coronagraphic imaging observations, and maybe even spectroscopic observations, depending on its separation and how good we get at using these modes. So again, you know, these are going to be really exciting opportunities to detect and characterize these planets. You know, this example I show here is simulated predictions for a sort of 300 Kelvin Saturn mass planet. That's something that's like an early analog to our own Saturn, you know, as if it was when it was born at sort of 10 million years. So characterizing these atmospheres is going to give us something that we haven't had before with transits or imaging. So I think it's going to be a really exciting opportunity. Okay, moving to the last section, spectroscopy. So similarly, you know, many of these objects, you don't necessarily need to use any high contrast imaging techniques, and you can perform direct spectroscopy. And there's a great reason to do that, right? There's just so much detail you get out of a spectrum. You can see here, this is for the sun. All of these individual lines give us a sort of different fingerprint for different atmospheric absorptions. So whenever we can leverage this technique and make the most of it, I think we really should. And I think there is potential to do this with JWST for imaging as well, for imaging exoplanets. So we explored this with the ERS program for something that's quite favorable to characterize through spectroscopy, VHS 1256b. Again, this is sort of more of a brown dwarf planetary mass companion, but in a very similar temperature regime to many of the exoplanets we're interested in studying, and really is an excellent analog to exoplanets in general. These atmospheres are really similar, so characterizing them is going to give us a great amount of constraining power on our own models that we can then pass down to the lower mass objects and learn more about them. So one great thing about VHS is it's separated from its host star at sort of 8 arc seconds. It means we don't even need to worry about the star. We can just put the spectroscopic IFU or slit directly on the object and start to characterize it across JWST's full wavelength range. So on the right here, this is what we had before JWST for VHS 1256b. You can see it's sort of similar story. We have decent characterization in the near infrared, and then we have something in the sort of 3 to 4 micron range. But beyond that, sort of no potential at all, or limited potential to sort of characterize this atmosphere. So that's what we did. You know, we leveraged the whole wavelength range, and we get this crazy spectra that I can't even fit on the screen really. And you see we characterize, again, this full luminous wavelength range. We're spanning multiple molecular features, multiple, you know, cloud features, and different aspects of the atmosphere. So the way to walk through this is not just in one plot. I kind of have to go through step by step. But if we go to these near infrared wavelengths again, like, you know, we're seeing these H2O absorption that we've already seen, absorption from CO, these nice potassium features actually that we're measuring are good analogs for the surface gravity of the object. If it was more massive, then these would be more heavily broadened. Moving to longer wavelengths, however, we start to see the really exciting new stuff that JWST is starting to show us. First, we have this really nice methane feature at sort of 3.3 microns. You can see closely matches the opacity we expect for the molecule at these wavelengths. And then similarly, which is, you know, my favorite feature really from the whole spectrum, is this insane carbon monoxide bandhead where we're resolving sort of every line of this opacity in our spectrum. So, you know, just on its own, this has great constraining potential, but also we can start to now think in terms of the interaction between different species. You know, methane and carbon monoxide are a common disequilibrium process. So by exploring, you know, the relative abundance of these two species can give us insights into not just, you know, what's in the atmosphere, but how is that atmosphere behaving and producing the molecules that we see. Moving slightly further out towards the Miri wavelengths, we see this really nice silicate feature. So in gray here, we have the data from VHS 1256b, and then we're comparing that to two observed spectra from different brown dwarfs, one with that silicate feature and one without. This is really exciting to see because it's an evidence for clouds in the atmosphere of this object that may be driving its variability through patchy cloud coverage, and is a really strong signal that we can start to detect this feature for lower mass objects as well and start to understand how clouds form in atmospheres and how they behave. So we can try and model this. We have tried to model this, but it's a learning curve. You know, when you have data of this high quality with this level of precision, it really limits our ability to kind of fit a single model to the data. You can see here in red, we have this model and it kind of, you know, matches the broad profile and maybe, you know, we understand where certain absorption should be, but actually trying to package that up into one single model that tells us, you know, this is the atmosphere of this object is proving quite difficult. So I think moving forward, you know, this data, the precision it provides and the wavelength coverage it provides is really going to give us this advantage at kind of nailing down these models in greater detail and trying to understand, you know, how do all these different aspects, disequilibrium chemistry, clouds, how do they interact with each other and actually produce the atmosphere that we see? Okay, you know, that's just for VHS 1256b, but really there's a lot more to think about as well. The brown dwarf population is much more numerous than the directly imaged planet population. So we can really start to characterize these objects across a wider range of temperature regimes to see how atmospheres evolve in temperature, and also start to figure out, you know, okay, how does disequilibrium chemistry respond to those changes? How do clouds respond to those changes? What drives the overall variance in atmospheres that we see across this population? Similarly, you know, we can start to dig into more detailed effects as well, like weather through variability of these objects in different observing bands, different features to see, you know, does the silicate cloud feature vary at the same time? Maybe the disequilibrium chemistry feature varies in the near infrared. And then this bottom one here, which I'll come back to in a minute, is really, you know, how far are we going to be able to push these spectroscopic modes? This is what we can do just now. And as Nicole was talking about earlier, you know, we should really be trying to push JWST to do things that maybe we weren't really thinking it was going to be able to do from the get-go. And I think we can do that for imaging. So to give you an example of this, here's a spectrum of a 450 Kelvin brown dwarf that just came out around a month ago. And you can already see how distinctly different the atmosphere is. You know, we're now dominated by a lot of methane absorption. We're seeing absorption from ammonia. And it's just giving us an idea of really what this different atmosphere looks like. So, you know, moving forward, I really do think we have this potential to sort of characterize all these different atmospheres, and we're already really doing it. Okay, so to give you an idea of this, pushing these modes to something that maybe we weren't expecting to do, here is an image in the top left, that's where I want you to focus just for now, of a IFU spectrum. So each pixel here is a spectrum of HR8799, this sort of canonical directly imaged system. It has 4 planets around it, but you're only seeing 3 in the field of view here. And what we can start to do is employ techniques from maybe other fields, particularly, you know, we've seen this for the cross-correlation technique used on transit planets a lot. We can take an image and not worry about, you know, subtracting any light from this system and just perform cross-correlation on each pixel in terms of, you know, an atmospheric model or specific species like H2O, CO, ammonia, methane, to kind of dig out, you know, are the planets there? And if they are there, what is the molecular sort of species that exist in their atmospheres? And so we really think we can do this to decent signal to noise. And these observations are already planned on the telescope to kind of explore this technique in greater detail. But beyond this, I think what is going to be really an exciting opportunity is that this is what I would consider maybe the worst case, you know, just being able to do this cross correlation. Just like we do with coronagraphy, this spatial profile of this star, we can also try and calibrate and subtract away to leave behind just the planets in this image. And this has already been successfully tested on some of the directly imaged objects, particularly YCs 1b and 1c, if you're familiar. I can't show you the spectra, but give us almost identical quality spectra that you saw for VHS 1256b, but for something that's sort of 6 Jupiter masses, a sort of true directly imaged planet. So to finish, I want to bring us back to this plot. And, you know, I mentioned we can start to look for these new planets. And maybe some of you saw this spectroscopy and you were thinking, you know, how are we going to do spectroscopy with the coronagraphs? Well, if we can push this spectroscopic IFU technique in greater detail and really try and drill down to sort of what is limiting our performance, then maybe we can get this sort of spectra as well. And the quality of that will really just depend on how far away the planet is from the star, rather than just like whether we can do it or not. Okay, so I'll finish there with some brief conclusions. You know, this really is a new opportunity for imaging in general, both in detecting new objects and characterizing the ones we already know about in new wavelength regimes and new atmospheric regimes. Spectroscopic observations are insane. Like whenever we can do that, we really should be. And I don't think we have anything that we're getting from JWST that really rivals the quality and the wavelength coverage that these direct imaging spectroscopy are giving us. And then, as sort of Nicole mentioned earlier as well, you know, this really is just a small slice of what we're doing. We have maybe 18 years more to look forward to, lots more to think about. So I think we can be very excited for the future. Okay, so I'll finish there, but yeah, happy to take any questions. Thanks.
Great, thanks, Aarynn. We have time for a couple of questions. Let's see, we have one right in front.
Thanks, Aarynn. That was great. This is Katie Bennett from Johns Hopkins University. I was just wondering, for the cross-correlation method then, do you need to have a good handle on the orbital parameters of those planets in order to predict where that feature is going to fall?
I mean, not necessarily, right? Because you're cross-correlating with every pixel. So, I mean, it helps in terms of, you know, if you know where the planet is, then you can be more sure that what you're detecting really is the planet. But there's no reason why you couldn't do sort of a blind search and just see, you know, are we seeing a feature in this image that corresponds to an atmosphere or a molecule?
Hey, Aarynn, great talk. I'm wondering, is there some kind of known or maybe unknown systematic that would prevent time series spectroscopy for several days of something like a lower signal to noise, colder Saturnish object in the coronography mode?
Yeah, it's a good question. What we do know actually is that the telescope is getting more and more stable by the day. And for imaging, that's really the main important thing for us. You know, how stable is that wavefront, our ability to characterize that spatial intensity profile between target and reference. So, you know, I don't know about maybe like a significant systematic that we think is going to stop us. I don't think that's necessarily the case. I think the bigger issue is going to be how significant do we think those variability like signals are going to be? And is that going to actually be something we can detect at the precision of the telescope? And I think maybe that's more of a maybe question, but practically, I think it's possible.
So I have two questions. The first question is, how do you think about the Roman CGI? Will it change the, would they open a new book?
Sorry, can you repeat that?
Roman CGI, Roman chronograph instrument. Yeah, do you think it will change the gain? It means that could we use it on the cold or warm Jupiter? Yeah, and the second question is, how do you thinking about a star shed? Yeah, because it's not mentioned here, but yes, another possible technique we can apply in next generation observation. Yeah.
Right. So I'll answer the second one first. There's no plans for like a star shade for JWST. I think maybe that's in the open for HWO. But yeah, that's certainly not for JWST. And then the first question I think was, and feel free to pull me up if I'm not answering this right. You're asking, you know, how is Roman CGI going to compare and how's that going to characterize I think Roman CGI's advantage is twofold. You know, first that's going to be looking in the optical. So that's going to give us an opportunity to maybe characterize the optical portion of these spectra for the first time, but also really I think is not going to do a huge number of objects. You know, from what I understand, Roman's going to maybe characterize 10 planets, and really the goal of Roman is more, let's test that technology so that we can apply it to future telescopes.
Okay, any more questions here? And one more online, Tracy?
Yes. So this question is asking, what is your thought for the theoretical modeling side to fit the detailed spectrum of the VHS 1256 minus 1257b?
Sure. There's the possibilities are kind of endless there. There's so much to think about. You know, this was always, that model I showed was always meant to be a quick, you know, what can we do right now with the data we have? Certainly, I think people in our team right now are exploring retrieval techniques to see how well they can do, although that's a whole difficulty in itself, just due to how many data points we have. Also, you know, maybe exploring 3D atmospheres rather than 1D atmospheres, trying to incorporate that variable cloud coverage and how that affects the atmosphere. And I'm sure more effects on top of that, like disequilibrium chemistry and how these all mesh together. You know, there's a lot to think about.